Let's start with a brief recap of what we have already done. We said that the condensate, or at least the fact that all the particles, or at least a large number of particles, behave like a single quantum state, can be modeled by a wave function like this. Strictly speaking, there's a non-trivial step here. After all, you have a multiple particles scenario, so your wave function should depend on the coordinates of multiple particles. What we are doing is we are actually replacing this by an effective single particle wave function, which looks like this. And from this, we had shown that if this is true, then the current, this of course is only pertaining to the superfluid state, not to the normal fluid part. And the current density that we calculated worked out to be h cross by m gradient of theta times n0. And since n0 here is essentially the superfluid density, and that tells us that the superfluid velocity field is basically h cross by m grad theta. And an immediate consequence that we talked about in the last class was curl of this is 0. So this is an irrotational velocity field. And this would, of course, this could have told you immediately that the circulation, which is Vs dot dr or dl integrated over a complete loop, looks like this should be 0, right? Because if curl of a vector field is 0, then the corresponding circulation from Stokes' theorem should be 0. However, this is not necessarily true for the simple reason that for this to work, what you need to do is this. You have to convert Vs dot dr into curl of V ds dot ds over the entire surface, right? So this circular integral, this closed contoured integral or a cyclic integral gets converted to a surface integral where sigma is nothing but as any surface, not necessarily the flat surface, but any surface which is bounded by this. Now, within a superfluid, curl of Vs is definitely 0. However, you could have a setup like this. You could have a superfluid between two concentric circular cylinders, right? You could have a situation like this where the superfluid is only here, which of course means curl of V is 0, but only in this region, the shaded region. Here, you cannot talk about curl of V at all. It's not even defined there. So you cannot really use Stokes' theorem to tell you that because curl of V is 0 in this region, the circulation is going to be 0, right? So in such a situation, you can actually have non-zero circulation. In fact, one way of producing such non-zero circulation would be something like this. So if you say start above the transition temperature, start above 2.17 Kelvin, and rotate this apparatus. So you have an apparatus where you have two concentric cylindrical cylinders, and you have the helium liquid in between the two. So you have it here, and you now start rotating it. Remember, above 2.17 Kelvin, helium is a normal fluid. It has viscosity. And when you rotate the cylinder, viscous drag between the cylinder walls and the fluid itself will make the fluid move, and it will ultimately move with the same angular velocity as the cylinders. So now you have a rotating liquid helium sample, but there's nothing wrong with that. Remember, this statement is true only, this statement about curl of V as being 0, etc., is only true for the superfluid fraction. Right now, you don't have superfluids, you have only a normal fluid. But what you can now do is you can slowly cool down the helium while keeping this turning. And then what will happen is some of the normal fluid will become superfluid, at least at the transition temperature. The superfluid fraction begins to build up, and as you go below the transition temperature, more and more superfluid begins to build up. And because of angular momentum conservation, some of the angular momentum of the normal fluid will be transferred to the superfluid. The important point is, this will of course make the superfluid also rotate. But the important point is, the superfluid cannot rotate with any velocity. Well, the velocity is not the important point, but the superfluid cannot rotate with an arbitrary amount of circulation. This kappa, the circulation, is not zero in such a case, but because Ps is this, the alternative calculation that we did the other day was kappa is simply going to be grad theta dot dr's integral over the complete loop, which simply will be h cross by m delta theta. Change in theta when you go all the way around the loop, and delta theta has to be 2 pi times an integer. So this will have to be an integer multiple of h by m. This was the flow quantization that we talked about. So the superconducting part of the fluid will pick up rotation, but will pick up rotation discretely. It will not immediately start to rotate. It will rotate only when enough angular momentum is available for it to pick up h by m, and then subsequently in units of h by m. Now this is something you can experimentally observe very easily here. So that's one consequence of the fact that superfluid flow is irrotational, and as a result, you end up with flux quantization for the superfluid flow. The superfluid does not take up any amount of angular momentum, it can only take up certain units, so that the circulation stays quantized as in units of h by m. Now, this is of course true when you have a fluid between two cylindrical regions. The way we are escaping this curl of V equal to 0 statement, or the way we are rather curl of V is 0, but the way we are escaping this implication that the circulation has to be 0 is via the fact that the vector field is not even defined everywhere inside the loop where we are calculating a circulation. So you take a loop here and you want to calculate the circulation along this. Stokes' theorem would have equated that to a surface integral of curl of V over this entire region, but curl of V is not even defined in the region inside. So that's how this problem gets solved. At least we don't have the problem that curl of V equal to 0 would have to tell you kappa is 0. But now, suppose instead of taking a situation system like this, suppose we had a cylinder of liquid helium, and we made that rotate. Okay. Now, in a normal fluid, what would happen if you were to rotate the vessel, of course, is that again viscous drag between the walls and the immediately neighboring liquid will make the immediately neighboring liquid, the liquid immediately adjacent to the walls, move around. That will make the next layer move around, that will make the next layer move around, and so the entire liquid will start moving, and ultimately the entire liquid will move with the same angular velocity as the walls. Okay. Now, what happens to the liquid surface in such a case? This is something which you studied in class 12 also perhaps, or at least somewhere in general properties of matter. If you have a rotating liquid in a vessel, what does the liquid surface look like?
The convex.
Okay, so it sort of bulges
It
up like
forms
this,
a
right?
vortex.
That's not a vortex. That's just a vortex is a spinning liquid in a tiny region. We are going to talk about what a vortex is. This basically is the shape of the surface instead of being flat changes. And what is this shape actually? There's an exact name for this shape. And indeed, it's a way of creating such shapes by spinning liquids. So it's a very important thing in many branches of physics, including optics, for example. It's a simple matter of balancing out the centripetal force needed at different points and calculating what the shape will look like. And it's easy to figure out that the shape will be a paraboloid of revolution, right? It will be, so this bulging shape that you have, this will form a paraboloid if it were rotating. Okay. Now this is what would happen in a normal fluid. Now, again, if every point is moving with the same angular velocity omega, then V at any distance r from the origin, from the center, would essentially be like this, right? If you take r anywhere on the axis of rotation, and if everything was spinning around with the angular velocity omega, the velocity of a given point will go like this. So, you know, all know this, right? This is a standard result in classical physics. And what is curl of such a V? That is curl of omega cross r. How much is this? Do you know the result? Or you may not know the result, but and the curl of A cross B formula is pretty non-trivial. Anybody remember the curl of A cross B's formula? If not, I never can remember the formula for a back minus cap doesn't really work that well here. That would have worked if this were a real vector product. After all, the derivative works on both and splits and works on the product by splitting it up first. So it's not really as simple as a back minus cap. Yeah. Okay. You may remember, you may not remember, but okay, let me just work it out for you. But does everybody know this notation?
Yes, sir. Levi-Civita.
You know what this is?
For the Levi-Civita.
Yeah, this is the Levi-Civita symbol, but what exactly is this? Epsilon ijk ei aj bk? Anybody recognize what this quantity is?
So does that stand for A cross B?
This is A cross B. If AJ and BK are components of a vector A and a vector B respectively, then this is actually A cross B. That's easy to see. For example, if you look at the I equal to, so I equal to 1, you can take I equal to 1, for example. This, of course, is sum over all I, J, and K values. So if you take the term with I equal to 1, you have E1, but then JK has to be either 2, 3 or 3, 2. Otherwise, epsilon I, JK will vanish. If it's 2, 3, you get A2, B3. If it's 3, 2, you get minus A3, B2 because epsilon 1, 3, 2 is minus 1. So that's just a term with I equal to 1. You can write down the rest of the terms and you'll see that this is nothing but the cross product, right? E1, E2, E3 are nothing but X, I hat, J hat, K hat. Okay. I hope all of you are familiar with this, right? If you're not, tell me.
Yes, sir.
Okay, so then curl basically goes the same way. It will be epsilon I, J, K, EI, del J, that's the jth component of the curl vector operator, times omega cross R's kth component. That's what you have to put in, right? And what's that? This will be epsilon KLM. The kth component of omega cross R is omega L Rm, but R's mth component is nothing but Xm, right? Now, when you do this, calculate this curl, this is pretty easy basically because when you're differentiating this, omega L is just a constant, so it doesn't get differentiated. There's only Xm which gets differentiated. So you have epsilon ijk, epsilon klm, ei, omega L that moves out. All of these are constants independent of X, so they move out. And how much is del J acting on Xm? Here you're going to get del J acting on Xm. How much is that?
So it will be delta Jn.
it will be delta JM. And now what I can do is sum up over M trivially using this delta. So this becomes epsilon IJK epsilon KLJ EI omega L. Right? I've just, when you sum up over delta JM, sum up over M, the M goes away everywhere else.
Yes, sir.
Gets replaced by a J. Now, anybody remember what this expression is? Or at least how much epsilon IJK epsilon
Delta IL it will be, sir.
KLM?
Oh,
This will be?
this relation will be sir, will I say that epsilon IJK or epsilon KM, that one, or the answer here?
Okay, you can say this if you know this, but maybe it's better to work it out from this. If you work it out from this, how much is it?
So that will be delta of IK, delta of uh, KL. Oh no, delta of IK. Sir,
Okay,
one
first
second.
thing you have to remember, will this result depend on K, the final result?
No, sir. K will.
K is a dummy index, right?
Yes.
K is being summed over.
Sir, it will
So
be
the result
delta of
will not have,
IK, delta of JM minus delta of
it can't have delta IK. Can't have a K. The final result can't have a K.
oh,
Okay, because K is summed over.
there is the common one. Yes. So that will be delta IL.
Basically, it's okay. Okay. Let me just help you out a bit because I deliberately wrote it this way, but it should better be written in this way. That way you know the formula. That is, the dummy index is in the same position in both. Remember, epsilon IJK and epsilon KIJ are exactly the same number, right? We cyclically permute the indices that does not change the value of epsilon. Okay? And the formula that you perhaps remember is the one in which the dummy index is the first one in both, or the last one in both. At least has to be in the same place. I wrote epsilon IJK epsilon KLM. There the K was in different places. You can figure out what's going to happen, but it's easier to figure it out by putting the K in the front. And then it's going to be delta, whatever you were saying. Actually, the first index in the second index here with the second index here, delta IL delta JM minus delta IM delta JM. That's the formula for the product of two epsilon summed up over K.
We leave out the common one and do the interchange and put the
Yeah,
delta
and then you typically easier to put the common one at the same place so that you can fall back on the standard result. Otherwise, you'll have to keep on thinking about sign changes and so on. But now, on the other hand, what we had was not this expression, but the expression where J was the same as M. Of course, when you say J was the same as M, you just don't mean that they're same, you also mean they're summed over. So what we had was delta IL, delta JJ, minus delta IJ, delta JL. Now tell me how much this is. What is this? What is delta JJ? Can anybody tell me that?
So that will be 1.
No, it will not be 1. The delta symbol is 1 if both the indices are equal. But delta JJ does not simply mean that you are making the two indices equal. It means that you are going to sum up over J as well. Remember, there is a summation convention here. Right? When you write this, when you wrote epsilon IJK, EI, AJ, BK as across, of course, I, J, and K were all summed over. So how much is this? Delta JJ? Is 3, right? Because there are 3 values of J. It's delta 1, 1 plus delta 2, 2 plus delta 3, 3. So that's P delta IL. How much is this?
That's delta IL.
That's delta IL. So this is actually 2 delta IL. This thing here. EI omega L. That's 2 EI omega I. Right? And what is EI omega I?
It's omega.
Is the omega vector. So this is twice omega vector. So when you have a rigid body rotating with an angular velocity omega, or a fluid rotating so that every part rotates with the same angular velocity, which is also for the time being like a rigid body, the curl of the velocity does not vanish. The curl of the velocity is actually twice the angular velocity. Okay. So this is something that has to be borne in mind, that rigid rotation of a fluid would violate the curl of V equal to 0 statement. So if you have a superfluid, say liquid helium near the absolute zero, where it's almost completely superfluid, would you expect it to be able to rotate like this? That is, the entire fluid rotating with the same angular velocity. The answer is no, because that would violate the curl of V equal to 0 condition. Okay? Yeah. So remember that if you are putting the liquid between two concentric shells, it can rotate with the shells, because curl of V is not 0 throughout in the region in between. If it's a normal fluid, of course, it can rotate with the shell. But once you cool it down to a superfluid scenario, it can only the superfluid part can only rotate by picking up finite discrete values for the circulation. That's because of this flow quantization thing, which is very similar to flux quantization that you have already studied in superconductors. But if you have a solid, well, okay, solid is the wrong word for it, but if you have a cylinder which is full of superfluid, you try rotating it, the superfluid rotating all as one piece, that would simply be impossible. Okay? So it would seem like if you took a superfluid and rotated it like this, the fluid will not move at all, because any rigid rotation would have a circulation, and you will have a flat surface. It will not become a concave surface and not become paraboloid. Okay? That's what it seems like, but that's not how it works. In reality, things don't happen that way. In reality, a superfluid also rotates, but in a rather different manner. The way it rotates basically is, and that's where what you were talking about comes in, vortices. What will happen is this: you will have a tiny region around which you will have the superfluid rotating. Now, your question could be, how is it possible that you can have even tiny vortices? Because after all, curl of V is 0 everywhere inside this loop, and wouldn't that actually invalidate a rotation? Remember, if the velocity rotates like this, then V dot dl will be positive throughout as you go around, and you will end up with a net non-zero V dot dl.
Yes, sir.
And okay, let me again stress that was not a problem when you had a fluid between two cylinders, because their curl of V was not 0 throughout inside. But here, you have a superfluid everywhere inside. So you would expect curl of V to be 0 everywhere inside this, and then you would expect the circulation to vanish. But there's a bit of a catch. The catch is superfluids are, of course, made out of actual material objects. And helium atoms are very strongly repulsive when they come very close to each other. The attraction between helium atoms is very weak, which is why they don't form a solid at atmospheric pressure. But they repel each other very, very highly if they come too close. Essentially, that means that although we were dealing with a continuum picture, we think of the whole thing as a continuum. But as you all know, any material medium is not a continuum. There are gaps because you have small regions inside. Here, if you have an atom of helium sitting somewhere inside, no other atom of helium will get close enough to that, because at least there will be a small region of this order of an angstrom in diameter, which will be completely excluded. So this continuum picture of a velocity flow simply cannot work out for the entire fluid. There will be small regions where you cannot have fluids. Okay. And it is because of these small regions where curl of V cannot vanish, simply because V will not be defined down to that level. You can have tiny rotating vortices. Of course, for each of these vortices, the flux is quantized. And so, in fact, okay, let me just do a small calculation for this. If you, any such vortex essentially would be rotating like this, and the best possible coordinate system to use for this, to describe this would be which one? Would it be easy to describe this using Cartesian or some other coordinate system?
Circular coordinate.
Which coordinate? Sorry, couldn't hear you.
Circular coordinate. Spherical coordinate.
Well, it's first of all circular. You mean polar, right? When you say circular,
Polar.
Yes.
polar
Yes.
coordinates. Well, polar coordinates is not very good, basically because we're dealing with 3 dimensions, so that's not really. Polar coordinates are of course intrinsically 2-dimensional. Spherical polar coordinates might be a possibility, but a much better thing is actually the polar coordinates in 3 dimensions. That is, polar coordinate extended with one additional coordinate along the axis here. So remember, your entire superfluid is actually rotating about an axis. So there's a cylindrical symmetry in this, right? The whole circuit is, whole picture is symmetrical about for rotations about this axis. So the best possible coordinate system to describe this in would be cylindrical coordinate system, a cylindrical polar. You were right about polar, except that because this is 3D, you need to add an extra the z coordinate, although that will really not make much of a difference here. But if you're using cylindrical polar coordinates and you want to calculate the curl, you would need to know the formula for the curl in cylindrical polar coordinates. Okay, let me just find out what that is. I can never remember that formula, but it's all thankfully it's always given at the back of a book. So I hope I remember this one. Let's see. Otherwise, I will have to go and search for a book. So you have R, phi, z as your cylindrical polar coordinates. I think I've got this. This is ER, R, E, phi, EZ. So it's very similar to the Cartesian formula for the curl, except that there are slight differences here. You have del R sitting here, del phi sitting here, del Z sitting here, just like del X, del Y, del Z. And then the difference is here you have VR, RB phi, and VZ. So the velocity vector Vs has 3 components, VR times ER plus V phi times E phi plus Vz times Ez. And this is the formula for the curl in cylindrical polar coordinates. Now, if we are talking about a cylindrically symmetrical situation where V depends only on R, that is, the components of V depend on nothing else, just depends on R, not on phi, and neither on Z because of the cylindrical symmetry. Then what do you, and in fact, that is precisely why we are using cylindrical polar coordinates. The description becomes simple because the result depends only on the distance from the axis, not on the angle which that line makes. Cylindrical polar coordinates could have been used, but they would have made the description of the symmetry more complicated. So then, if you look at this, V depends only on R, not on phi, not on Z. So any term with del phi, del Z, you can simply ignore. Okay. So one term in the curve, the Ez term, what will that be? There's a 1 by R outside. Ez will have a del R of R V phi, right? There would of course be also be a minus del phi of VR, but that term would be 0. Okay, right?
Yes, sir.
There would also be an E phi term from here that would involve del R of Vz, but if the fluid is flowing in a around the axis, it's not actually moving up, so there's no Vz component. So this essentially will be the whole thing. So for this to be 0, what you need is this. In fact, you can actually drop the del, you can change the del R's to ddRs. Because it depends only on R. So what does this tell you about V phi? This is a trivial thing to integrate, right?
So then V
And solve.
phi is a
V must
constant.
be 0.
No, V phi will be a
V phi is a constant is not really right. The V phi is a constant would be very horrible, right? It would mean that no matter how far away from the axis you are, you have the same velocity. That would be horribly wrong.
V phi must be
What
0.
is it? No, if V phi must be 0, then that's a possibility that the fluid doesn't rotate at all. That's not the possibility we are looking at. What other possibility is possible there?
So V phi would be like some constant divided by R.
Exactly. It will be a constant divided by R, right? R V phi should be a constant, not V phi. This equation really says that the rate at which R V phi changes with R is 0. So R V phi should be a constant. So it should be 1 by R. In fact, in terms of the circulation, which is quantized, so it's a nice thing to talk about. Kappa by is actually kappa by 2 pi R, and that's it. Right? So the velocity of the superfluid will be essentially like you do realize why it should be kappa by 2 pi R? Yes? As you have said, V phi should be some constant by R, right? But if V phi is constant by R, how much is kappa? The circulation. What's the easiest way to calculate the circulation? You take a circle of radius R and calculate the circulation of this velocity, which is of course tangential at every point. How much will that come out to be? Okay, everybody has got the fact that V phi is constant by R.
Yes,
Is that
sir.
okay?
Yes, sir.
Then velocity vector is constant by R times E phi. That's understood,
Yes, sir.
right? So what should this be? V dot dr. When you are moving in a circle, what is the dr vector? That's a vector which is tangential. And how long is it? It's actually, if the length is, if this angle is d phi, the length is r d phi, right? Is that okay?
Yes, sir.
Okay, so I made a mistake here. It cannot be v dot dr by r. It's just v dot dr. What I meant was c by r e phi dot dr. Right? That previous statement that I wrote was completely absurd. V dot dr, of course, is v dot dr, not v dot dr by r. But this is what we meant. Okay. But what is e phi dot dr? It's nothing but this length, right? and that's R d phi. So C by R into R d phi. And when you go all the way around, okay, this is a closed contour integral. You go all the way around. How much does phi change when you go all the way down?
2 pi.
2 pi.
So this integral is 2 pi times C, right? So kappa, the circulation is 2 pi times C. And all I've done here is rewritten this V phi, which is C by R, as kappa by 2 pi by R. That's what I've done here. Is that okay?
Yes, sir.
Yes, sir.
Okay. So basically, if you have a velocity field like this, what you're going to get is curl of Vs will be 0. Remember, that's what we solved. But will it be 0 everywhere? This is what curl of Vs is for a cylindrical symmetrical velocity field. Okay. And from the fact that it's 0, we deduce that V phi has to be C by R, hence keep kappa by 2 pi R. My question is now the other way around. If you know that this is your this V phi is C by R, does that mean curl of Vs is 0? Yes?
Yes, sir.
Well, almost except at one point, which is, well, remember, this how did we manage to escape the fact that zero curl would have told you that there is no curl, no circulation. If the curl had been 0 really throughout, there would have been no circulation. Stokes theorem. Nothing much more you can do about it, right? But here you are getting a circulation, right? Kappa is 2 pi C. So there is a non-zero flow and there is a circulation. So how can you get a non-zero circulation if curl of Ps is 0 everywhere?
Sir, can you please repeat once again?
So this whole thing has been like this. For superfluid, Vs is irrotational, so its curl is 0. If the curl is 0 everywhere, then the circulation kappa has to be 0 because Stokes theorem would tell you that.
Yes, sir.
What we need to see that if you have a fluid between two cylinders, then curl is 0 only where the fluid is, not elsewhere. So you did not have to have circulation 0. In fact, you had flux flow quantization there. Okay, because delta theta could only change by delta theta could only be 2 pi or its multiples. Here you have fluid throughout. So curl of V is apparently 0 throughout. If that were the case, then the circulation would have to be 0 throughout. But what we have done is we have solved the curl of V equal to 0 equation apparently. We have just solved this equation, landed up with the statement that V phi is C by R, and then calculated that, okay, given this C, kappa would have a particular value, that's 2 pi times C. So you can rewrite everything in terms of kappa, so you get kappa by 2 pi R, a non-zero kappa. Okay. Now this is where the contradiction is. After all, if you have a curl of V which is everywhere 0, then you cannot have a non-zero kappa. So how come? So apparently you have solved curl of V equal to 0 to find out a velocity field like this, but then it's actually contradicting kappa equal to 0.
Then, sir, we have got wrong value for V's of phi.
Okay, one possibility is we have made a mistake, right? That's of course always a possibility that V pi cannot be this. That is, the superfluid surface simply cannot move. However, we did this calculation, right? This is This is all we did. If this is to be 0, RV phi has to be constant. That's all we use. So what's wrong with that? Or the other thing is, of course, would be to check with experiments. Does a superfluid surface actually rotate when you rotate the cylinder? The answer is yes, it does. So everything boils down to the fact that if V phi is constant by R, is this thing actually equal to 0? Yes? That's
So
an easy question.
put
Yeah,
V
go ahead.
equals to C by R, then it is always 0. But if it is not C, means if it is something
No,
like
no.
some,
It has to be a constant, right? You are just putting that in. That's your
yeah,
solution.
yes, sir.
So you're claiming that if that is true, then it's always 0.
Yes.
There is something very simple which is staring you right in the face, which you're missing because it's perhaps too simple. You're focusing only on this. Remember, the curl component is this, the whole thing. Yes? Come on, there's a 1 by R in the front, right? Doesn't that tell you something? Your claim is curl of Vs is 0 for this kind of flow. And you would be right, except at one point. You're dividing by R, right? That's something which you're not allowed to do if R is 0. You get that?
Yes, sir.
Yes.
So here the point is the curl vanishes everywhere except at R equal to 0. Of course, R equal to 0 is a point, but remember, whenever we say things like velocity field or even density or stuff like that for continuum media, we are actually making an approximation. An infinitesimal volume or an infinitesimal distance in a real substance is not really a mathematically infinitesimal region, right? When you say something like mass is integral of rho dV, where rho is the density, is this dV really an infinitesimal volume? Can it be? Because if you really probe very, very far down, you will find that there is no smooth density at all. The density fluctuates widely. After all, if you go down to the atomic level, you will find a nucleus where there's a huge amount of mass, right next to it there's no mass, right next to it there's a huge amount of mass again, and you get all kinds of highly complicated bumps all over the place, right? So when you use things like charge density, mass density, velocity field, all these concepts for continuum physics, you actually are considering a physics infinitesimal. It's not really a proper infinitesimal. It's still a large enough region where you can have millions and millions of atoms, but small compared to the macroscopic world. That's what our infinitesimal is. Here also, when you say R equal to 0, you don't really mean R equals 0 exactly. But basically, curl of Vs is 0 except at R equal to 0 mathematically, but except at what is something which is called the vortex core. A tiny region around where the superfluid density essentially vanishes. Okay. Remember, our entire thing about all this thing came from this, right? Now, This is something I asked you the last day also. This is a complex number. Does every complex number have a well-defined magnitude and a well-defined phase?
Yes, sir. Every complex number have a well-defined magnitude and a well-defined phase.
Well, not really. We talked about that also. There's only one exception to that statement. Of course, phase
Zero.
is never well defined. Phase is defined only up to modulo 2 pi, but that's fine. It is locally well defined. But there's one now complex number for which the phase is not even defined, which is yes. You all know that. Zero. Zero does not have a well defined phase, right? If the magnitude is zero, any theta that you put in will give you the same result. Okay. You cannot say that the phase is this much, not even modulo 2 pi. Okay. So in the vertex core, psi 0 vanishes because there is no superfluid just in the vertex core. And as a result, theta becomes ill-defined at the vertex core. So note that curl of V equal to 0 did not lead to zero circulation for our cylinder case because there was no superfluid inside the two cylinders. Here, essentially the superfluid density vanishes in the vortex core, which is a tiny region, which is a region of the order of 1 angstrom each. And this is why you can actually have non-zero circulation. Okay. Right? So
Yes, sir.
basically, if you plot the superfluid current, or this current, of course, is not electrical current, there's a mass current, you have behavior which is like this. Up beyond 1 angstrom, the superfluid current is, of course, proportional to the velocity. So the velocity drops off as 1 by r. You get a sort of 1 by r behavior here. But close to the core, the current drops drastically to 0. Okay. So inside the core, which is a very tiny region, there is no flowing superfluid. Outside, you have a superfluid circulating around. And the velocity keeps on decreasing as you move further and further away. Okay. Now, typically, and this is something which we cannot really talk about right now because we have not talked about the energetics of the problem. We have not said how much energy is required to produce these vertices. But let me just tell you that it takes energy to produce vertices. And remember, this kappa, as we said, was quantized in units of h by m. So circulation per vertex would typically be sort of close to the lowest possible value. If it's not, if it's, it can be, of course, be zero. It can be zero, but kappa typically is of the order of h by m. Higher order excitations, 2h by m, 3h by m, that hardly ever occurs because that takes a lot of energy. Okay. Now this means that we have a bit of a problem left because when you talk of suppose you look at the cross section of this rotating fluid, the entire thing is rotating. So near the surface, the velocity of the superfluid essentially is omega r, where r is the radius of this cylinder. Okay. So what is the flux? What is the circulation of the fluid in this region? Quickly, how do you get the circulation if it's omega r throughout here like this? Remember, you have to do v dot dr. But here, if you take a loop which follows this contour, dr and v are in the same direction. So v dot dr is simply v dr integrated. And v is constant at omega r on this outer loop. So how much is the net circulation? It's just V into the total length, which is 2 pi epsilon r, right? So that's the circulation. Okay. Now this can be very huge because this is a macroscopic object circulating with some omega, right? Some finite omega, and R could be quite big, okay, maybe a few centimeters. So this is a pretty big, large number. Whereas our kappa is of the order of h by m, which is very, very tiny. How do you resolve the two things? Do you understand my point? We just figured out that you have a vortex. You can have possible vortices where the velocity sort of goes like this. You have a region in between where there is no superfluid, that is, superfluid density falls out to zero. Then you have velocity, which decreases as you move out. So there's a spinning vortex kind of thing. The superfluid keeps on spinning around the vortex core. But to create a vortex requires energy, and typically you create it at the lowest levels of excitation, which is of the order of h by m. Even if you somehow manage to excite higher order flow quantization, so 2h by m, 3h by m, that's still a microscopically small number compared to the circulation that the fluid actually has, which is 2 pi omega into r square, which can be quite huge, macroscopically large. So whereas a vortex can essentially only have a circulation like this, the fluid has a much larger circulation. How is that possible? The answer is absolutely trivial, by the way. How is it possible that the fluid has such a huge circulation without, despite the fact that you can only have a microscopic amount of circulation per vortex? But I actually gave out the answer right now. I've actually given you the answer right now. Yes? Okay, let me just couch the question in a slightly different manner. This has nothing to do with superfluids. This is just a standard statement about this integral, P dot dr integral. Suppose you know that you have, let's say, two vortices, V1 and V2. Suppose you're in the entire system, there are only two vortices. So there are 2 points, two vortex cores here, where you do not obey curl of V equal to 0. Just at these 2 points. Everywhere else, curl of V is 0. Now the velocity on this particular large circle here can be very different from the velocity here and the velocity here, right? As you remember, even for a given vortex, the velocity decreases as you move away from the center of the vortex. Now the question is, can you tell me how much is the circulation of this vector field V along this loop if you know the circulation kappa 1 here and the circulation kappa 2 here? That is, how much is this integral if you know, so this integral over this contour gamma, if you know these two. So this is known, and this is known. Can you tell me how much this integral is? That sounds almost impossible, by the way, because Because this velocity, of course, is very different from these two velocities. But you know one thing, you know in this entire region, curl of V is 0, except at these two vortex cores. I would ask you to cast your mind back to first year in college, first year mathematical physics, where you did things like line integrals like this. Am I still connected, by the way?
Yes, sir.
Okay, I think you've all done this, but let me just remind you. Okay, suppose you had these two regions where you had non-zero possible curl, but everywhere else curl was 0, and you wanted the circulation about this path, this big circle, but instead of going through the entire circle, you could go like this, right? Does this remind you of something?
Yes, sir, yes.
What will be, okay? What will the circulation about this path be? You're going like this, right? How much is the circulation along this new contour? Come on. What is curl of V everywhere inside this contour? Okay, let me rephrase. These 2 points, which are marked with crosses here, where the curl of V is ill-defined. So, are they inside the contour or outside the contour?
Outside.
Okay. So, inside the contour, everywhere curl of V is how much? 0.
0.
0.
So, what should the circulation be for this big contour? Let me remind you once again, V dot dl is curl of V dot ds. So if curl of V is 0 everywhere inside the contour and it's ill-defined nowhere, it's defined everywhere and it's 0 everywhere inside the contour, how much should the line integral be?
0.
0. Exactly. So this, for this big deformed contour, the line integral is 0. But then what you do is you punch this in, you know that you essentially pinch this side with this side so that this becomes a closed circle. This also becomes a closed circle. And these two, so basically, okay, maybe I will try drawing a bit, but although my drawing skills are very bad. So what you do is you go in, you go all the way round, and then you go back and then continue. That means these two cancel each other out, and this becomes the full contour. Same, you can do the same here. So what does it tell you about this circulation? Circulation of this in this big contour in terms of these two. Here it is telling you that if you were to add this circulation with this one and this one, right? Because remember, this is how you're going around. The sum total of these three circulations have to be, once you pinch this in, it essentially looks like this, right? So going like this, then coming in, then going like this, then coming back along the same path, then going like this, down, this way, back, right? So what is the sum total of this contour and this one and this one? Yes? Come on, you worked it out right now. What is the circulation for this?
0.
So what is the sum of this circulation and this circulation and this circulation?
So 0.
Right? Which means that the circulation over the bigger loop is actually negative of the sum of these two inner circulations, right?
Yes, sir.
But these are actually going the other way. These loops are actually now clockwise as opposed to counterclockwise. So if you were to take all the loops counterclockwise, you would simply end up with this circulation over the bigger loop is simply kappa 1 plus kappa 2. That's the sum. In fact, if you had more vortices, more vortex cores, then once again you cannot say V equal to kappa 1 plus kappa 2, but what you could do is use a very similar argument by pinching it everywhere and going around and so on, around every one of the cores. You have to avoid every one of the vortex cores because that's where color V is not 0. And then you will see that the total circulation about the big loop, which we found to be this much, has to be the sum of the circulations of all the vortices. Okay. So how can you have a large circulation despite the fact that circulation is quantized in h by m? And typically a vortex only has a circulation of h by m, or maybe a small multiple of that. The answer simply is have many vortices. So basically what happens is this fluid ends up having many vortices inside. So instead of flowing like a rigid body where everything moves with the same angular velocity about the axis, the superfluid breaks up into many tiny vortices, so that the net circulation 2 pi omega r square actually is achieved despite the fact that each vortex has only a very tiny microscopic amount of circulation. Got it? In fact,
Yes, sir.
and easily, by assuming that the vortex is only excited to its lowest degree, that is kappa is actually exactly h by m and not a multiple, you can get the number of vortices from here. Okay. So the larger the cylinder, larger the cylindrical cross section, larger the, so you end up with NV is 2 pi omega r square by h by m, right? And pi r square, so NV by area, pi r square is the cross section area. So density of vortices, number of vortices per unit area is twice m omega by h. Sorry, not h cross, h. So this gives you the number of vortices per unit area produced in a rotating cylinder full of superfluid, where omega, of course, is the angular velocity of the superfluid. So faster you spin the fluid, more vortices are created. Yeah.
Yes, sir.
And okay, to go beyond this, this is not the end of the story, of course. The vortices require energy to create. There are vortex-vortex interactions in a superfluid. Those are more advanced stuff. We are not going to talk too much about that. One thing I can tell you is that if you were to do the energetics right, that is, if you take the vortex-vortex interactions also into account and calculate the energy properly, a very interesting result comes in. It turns out that the vortices tend to form a lattice of their own. They form to sit on the vertices of a triangular lattice, because that's the one which minimizes the energy the most. So you end up with a vortex structure looking like this, which of course is also often called a hexagonal pattern. So in a superfluid, if you were to observe it carefully and measure where the vortices are, you would find vortices being, in fact, you can actually see these vortices by special means, and you can see the vortices form a nice hexagonal beehive-like structure. And that's basically because that's what rewards the energy the most. We are not going to go into details of how to prove that, because we are not going to discuss vortex interactions and stuff like that. Okay. But basic idea here is you have to realize clearly how you can have vortices and circulation despite having curl of V equal to 0. Curl of V equal to 0 is a statement which is valid as long as you have, ultimately we started with this macroscopic wave function, right? We started with this chi equal to root over n0r to the I theta r. And there we ended up with J is proportional to grad theta, so Vs is like grad theta, and so curl of Vs is 0. All this is fine, except that it breaks down where theta is not defined, and that happens when n0r is 0. So vortex cores are basically places where there is no very tiny places where there is no superfluid, and you have circulating fields around that. Okay. Now the same structure will also repeat in superconductors almost identically. So we will talk about that then. Okay. Now, unfortunately, I don't think I will be able to finish off whatever I wanted to do today. But let me just quickly, so I will need one more day to talk about superfluids before we go to superconductors. But let me just point out one more thing at least. And this is Landau's beautiful theory about critical velocity. Okay. Now, and this will also explain why Landau did not believe that Bose-Einstein condensation was at the heart of superfluidity when he first discussed this theory. He has later been shown not to be perfectly right if a Feynman had actually shown how Landau's theory would still work even with the Bose-Einstein condensate. But for the time being, let's just follow Landau's original argument, which is actually quite beautiful. The basic idea is something like this. Landau was asking himself the question that if you have a pipe through which a superfluid is flowing, how can the superfluid actually lose its velocity? That is, rather, how can the superfluid not be a superfluid? Okay. So you have a fluid flowing through. Of course, you would say that the surface of the pipe, which is not perfectly smooth, essentially produces a perturbing potential on the fluid, and that is what is going to act on the fluid at a microscopic level, right? The fact that you have imperfections on the surface of the pipes, they are not exactly smooth, that will produce this effect, that it will make the superfluid lose energy, or rather it will make the fluid lose energy. Right? I'm going to talk about this argument in the next class because I don't think I will be able to complete this argument if I hurry too much. But let me just point out one thing. The critical result which Landau needed was energy of a system. Okay, is that frame dependent or frame independent? Let's ask you that. Let's settle that question today. We will use that in the next class. Is the energy of a system dependent on the frame or independent of the frame? Yes? When I say frame, I mean frame of reference.
Yes, sir.
What? Yes meaning what? Yes, it depends, or yes, it does not depend?
So it depends.
Depends, right? Of course, the velocity depends on the frame, so the energy, of course, depends on the frame, even the kinetic energy.
Yes,
But do you
sir.
know how the energy changes from one frame to another? Well, at least you must have learned this in special relativity, right? That energy and momentum form parts and four vector. So when you go from one inertial observer to another, the energy and momentum gets mixed up among each other. You know about this vector, right? E by C P vector, which is the energy momentum 4 vector.
Yes, yes, sir.
And when you say something is a 4 vector, what do you really mean? You mean that when you go from one coordinate system to another, that is one inertial frame to another, the components of this 4 vector changes in exactly the same way as the components of space-time, that is, these change. So when CT comma R vector undergo a Lorentz transformation, E by C comma P vector also undergoes a Lorentz transformation. So this actually tells you how energy changes when you go from one frame to another. But we are really interested in what happens at a macroscopic level, for at least what happens at non-relativistic speeds. So we are really looking at Galilean transformations and not really Lorentz transformations. Now, it's somewhat funny that it's actually better. The energy momentum transformations are perhaps better known for Lorentz transformations than for Galilean transformations. And of course, you can find out the Galilean transformation result by taking the appropriate limit of the Lorentz transformation result. But let me try to show you how this works using a much simpler argument. Suppose in one frame you have a fluid of mass m with velocity capital V. Okay. The kinetic energy of the fluid in that frame would be right. Is that okay?
Yes, sir.
So this is the kinetic energy in the original frame. Let's say you're in another frame which is moving at a speed small v with respect to this one. So what will the velocity of the fluid be in that frame? Yes? Come on, the velocity of the fluid in the original frame is capital V. If this is moving at small v, the velocity in that frame will be how much? Right? This is capital V minus V, the relativistic velocity, the relative velocity, right? And the energy, kinetic energy we'll see from this frame is E given by half m v minus v whole square. Okay? So basically, what you have is E0, if you square this out, minus another term, which is how much? Right? So this is a momentum dot velocity. Okay?
Yes,
This is
sir.
how energy transforms. If energy is E0 in one frame, in another frame moving with a velocity v with respect to that, the energy will become E0 plus half mv square minus p dot v, where p is the momentum in the original frame. Okay? Right?
Yes.
I've just used kinetic energy as an example, but after all energy momentum transforms in the same manner. So I've just used kinetic energy to figure this out simply. Then, of course, start with the Lorentz transformations between E by C and P and take the appropriate limit of low velocities and deduce that this is going to be the case. But now, okay, let me just quickly give you the basic stuff of Landau's argument, although I'm going to talk about that in more detail later. Landau essentially said this: how can a fluid flowing through a pipe lose energy? After all, here we are thinking of a fluid which is essentially in one quantum state. Remember, we have a narrow capillary tube, it's only the superfluid which flows inside. The rest of the normal fluid stays back. And the superfluid essentially is a single quantum state. And as such, its energy is just the ground state energy. It cannot change. So changes in energy, which is caused when the wall actually acts on it, the wall has to be able to decrease its energy. And for that, what would happen is that there has to be a quasi-particle excited out of the fluid. Okay, so everything was in a ground state, it has to be excited to a new state. You have studied quasi-particles already, right? Phonons, for example, or magnons, maybe not yet, but maybe around just now.
Yes, sir.
So basically, these are low-lying excitations in a field which happens and which essentially gives you the excited energy levels. They behave like tiny particles. They're not exact particles. They're not exactly particles because they don't have all the particle properties. But energy changes in discrete units. Sometimes momentum changes in discrete units. So you call them quasi-particles. And in superfluids, like in superconductors, that's why we are going to finish this after talking about superconductors. You can figure out using the Bogoliubov method that there will be excitations over the ground state. Okay. So right now you don't need to know the details of the excitation. All you need to know is if an excitation is produced, it has a momentum p. It's like a tiny particle with a momentum p and an energy which depends on its momentum. So there's this, of course, this is the dispersion relation, which we have already perhaps worked out for phonons, and maybe you're in the process of working on. I don't know where ma'am is with this, but maybe you already may have worked out the dispersion relation at least for the ferromagnetic chain, right? Have you? Magnon dispersion relations and so on.
Yes, sir.
So basically, depending on the nature of the interactions, okay, depending on the details of the nature of the interaction, of course, you will have a quasi-particle excitation spectrum. The quasi-particle will be produced with a momentum p and an energy epsilon p. Okay. Now this is in the rest frame of the fluid. Of course, the fluid is flowing. In the rest frame of the fluid is stationary. It's the walls which are moving, and the interaction with the walls, let's say, is creating a excitation which has momentum small p and energy epsilon p, which of course is a function of this p, okay, or at least the magnitude of the p. Now this is, so in the frame of the fluid, you now have energy epsilon p, okay, plus E0, where this is, okay, let's not confuse this E0 with this one. This E0 here is just the ground state energy. So this fluid is moving with respect to the tube in the velocity v. And in this fluid, you have created an excitation. So its energy is now E0 plus epsilon. Okay. So now, if you were to go to the rest frame of the tube, what is the velocity of the rest frame of the tube with respect to the fluid? Again, very simple question. The fluid is moving with velocity v with respect to the tube. The tube is moving with velocity what with respect to the fluid?
Minus V.
Minus v. So you are now changing from one frame where the fluid was at rest, where the energy was this, to another frame where the fluid is moving with velocity v and the tube is at rest. Now I've already given you the energy transformation rule. E goes to E0 minus P dot V plus half mv square. So what will that go to? So this is in the fluid frame once the excitation has occurred, and in the tube's rest frame, what's the energy? Remember this quantity, okay, maybe I will not write this as E0. Let's write this as E ground or whatever. This is my E0. Note that this is how energy in two frames are related to each other. So what will you have here? Yes? Let's use this formula. What will it be? This formula tells you, if you know the energy in one frame, how to calculate the energy in another frame, which is moving with respect to the first one. Here you know that the energy in the fluid frame is given by this. Once the quasi-particle has been created. What is the energy in tube's rest frame?
So E naught plus
Okay, E naught is Eg plus epsilon P. That's E naught. Okay. Then
plus P dot V.
plus P dot V, not minus P dot V. That's good. Because the velocity is minus V here. And the next rest of the term is actually half mv squared. So minus V squared is also V squared, right?
Yes, sir.
So in the tube's rest frame, the energy after the quasi-particle is excited is given by this whole expression. Before the quasi-particle was excited, what was the energy? This is, of course, the energy of the fluid, right, in the tube's rest frame. Before the quasi-particle was excited, how much would the energy be?
Only EG.
No. Only Eg is the
Ground
energy
state.
in the fluid's frame. Okay, how much is the momentum in the fluid's frame? How much is the momentum of the fluid in the fluid's frame?
0.
0. So the P dot V term now will. Remember, this is a momentum which has now come in because the quasi-particle has momentum, right? The fluid doesn't have a momentum in its own frame. So before the quasi-particle was excited, this was the energy. This plus this.
Okay.
But it's easy to see. If the quasi-particle was not created, this term would not be there, this term would not be there. That's it, right? But now Landau made a brilliant observation here, which was like this. Will you expect the energy of the fluid to go up because of the excitation or go down? In the tube's rest frame, would you expect the energy of the fluid to go up? In the fluid's frame, the tube is acting on it and producing an interaction, producing a effect, and the excitation is being created. Of course, in the fluid's frame, creation of the quasi-particle increases the energy, no problem about that. But if in the tube's rest frame, the tube, the energy of the fluid actually increased because of the excitation possible, then what would happen? Note that the tube is at rest. It's only the fluid which is flowing, and the interaction with the tube has increased the energy by causing an excitation. Then it could cause another excitation, increase the energy still further. Another excitation, increase the energy still further. That way you could get energy out of nothing, right?
Yes, sir.
So that's not possible. So what, and this is a brilliant part about Landau's argument. He said that in the tube's rest frame, excitation can only decrease the energy of the fluid, overall energy of the system. And that's the only way this excitation can occur. Therefore, for the excitation to occur, you must have this. Okay. So what does it tell you about the momentum P? If this is to be negative, epsilon P is the energy of the quasi-particle. It of course is positive. You had a ground state, the quasi-particle is an excitation, which means the energy has gone above. The epsilon P is of course positive. If this epsilon P plus P dot V is to be negative, what does it tell you about P dot V first of all?
So P should be negative then.
Well, P is negative. P is a vector. Saying that it's negative doesn't really make much sense. Vectors don't have positive or negative vectors, right?
Mass should be negative then.
No, no, no. That's not what is being said. It says dot product, right? It's P dot V. P dot V has to be negative, not P. P dot V is a number, of course, that can be negative. And what does it tell you physically? It tells you that the quasi-particle can only be created in the direction opposite. That is, it can
Theta
only be
should be
created with the momentum
180.
opposite the velocity.
Or theta
Okay.
should be 180.
Well, one more than 90 at least. Not necessarily
I know.
180, it's not necessarily
Yeah,
one
yeah.
dimensional, but it has to be created opposing the fluid flow. So if the fluid is flowing to the right, the quasi-particles created have to be created moving to the left. Okay. But it also tells you one thing. If say, if this result, epsilon p by mod p, okay, if this ratio had a minimum, if this were true, if epsilon p by mod p had a non-zero minimum and we were smaller than that, would you be able to satisfy this relation? What is the maximum possible, or what is the minimum possible value, or maximum possible value magnitude y of p dot v? P dot v is, of course, pv cos theta, right? So the least it can be is minus p times v. Okay, right?
Yes, sir.
And so in order that this become negative, p times v has to be bigger than epsilon p, or v has to be bigger than epsilon p by p. So if it so happens that v is less than this minimum, then can you ever satisfy this condition? Yes? Come on, quickly. I'm just talking about this, whether this can ever exceed this in size. A dot product of two vectors, can it exceed epsilon p? That's the question. In size. You can get a minus, you of course need a minus sign for the dot product.
No, sir.
No, right? If v is less than this. So what Landau could argue is that a superfluid, if we are flowing fast through a tube, so fast that we exceeded this minimum value, then it would be possible for interactions with the tube to produce excitations in the superfluid that would actually take it out of the condensate state. Okay, he wasn't calling it condensate, but he would be taking it out of the macroscopic state, and then you would actually get the normal fluid part. The superfluid will lose its superfluidity. It would lose energy, basically, interacting with the tube. Okay. However, if the velocity of the fluid was less than this minimum value, then it's impossible for the interaction to create an excitation, because then it would never be possible for the fluid's energy to decrease by creation of this excitation. Right? Clear?
Yes, sir.
So what Landau figured out is that for superfluid flow, there would be a critical velocity. So if v is less than vc, which is given by the minimum over all possible values of the momentum of epsilon p by p, then the liquid will flow without viscosity. So this is the argument that Landau gave, saying two things. Saying that fluid flow in a superfluid flow will have a critical velocity. If you were to move too fast, you would be able to create excitations and slow down the fluid as a result, and superfluidity will be lost. But he also said that, okay, this puts a restriction on the kind of dispersion relation X and P you can have. Why? For the Bose-Einstein condensate or free particle, okay, not the Bose-Einstein condensate, but for the free particle Bose-Einstein gas, the condensate, of course, is the macroscopic occupation of the ground state. The excitations are the levels above that. But for a free particle gas, how is epsilon P related to P? The momentum? What is the energy? Energy is given by h cross square k square by twice m, right? The momentum is simply h cross k. And you know the relationship, the reason why they are related in this way is actually epsilon obeys the non-relativistic formula, p square by twice m, right? Is that okay?
Yes, sir.
So XNP for the free Bose gas, this is what?
Parabolic.
It's a parabolic curve. XNP is p square by twice m. But can anybody tell me what is the VC then, critical velocity for this? If you divide epsilon p by p, what do you get? P by twice m.
Yes, sir.
And then, what is the minimum value? What's the minimum possible in a momentum that you can have? Yes?
0.
0. Right. So, or you might say that because of periodic boundary condition, there is actually 2 pi by L lower limit for the K, right? Because the ground state is n equal to 0. Anything excited would have some momentum, but that momentum would be vanishingly small in the limit of large F. So what does this tell you about Landau's criteria? What is the critical velocity for this free Bose-Einstein gas? It's 0, right? So according to Landau's argument, a free Bose-Einstein gas simply cannot be a superfluid because the dispersion relation epsilon p equals p square by twice m does not allow you to have a non-zero critical velocity. Remember, I said that although London and Pisa had assumed that the superfluid part is actually a Bose-Einstein condensate, Landau was strongly against that. He was strongly against that for many reasons. One of them was the fact that the heat capacity divergence is not there in a Bose gas. It's a cusp, not a divergence for Bose gas, for a free particle Bose gas. He was also against that simply because of this reason. Because a free Bose gas simply cannot become a superfluid, even in its condensate state. It is the whole point is there are too many low energy excitations available so that the system will get excited and lose its energy that way very, very rapidly. Got it?
Yes, sir.
Of course, this means that Landau had to propose that the actual dispersion relation for a superfluid would have to be different. And we're going to come to that in the next class, but let me just quickly point out one thing. Suppose you could use instead of using free particle picture, if you use a phonon picture, you know what the epsilon p is like for a phonon versus p? You have seen the graph, right? Epsilon k versus, there you called it epsilon k versus k. For the acoustic branch, what does it look like? Okay, maybe we'll talk about that in the next class. But let me just say that, let's say hypothetically we have a x and p versus p graph which looks like this. This ratio, what is this? Geometrically, what is this? X and p by p. This ratio, what is this?
Decaying graph.
Hmm? No, I'm saying forget about the physical meaning of x and p. If you have a y versus x graph and you ask y by x, I'm not talking about the minimum value, I'm just saying y by x at any given point. For any point on the graph, if you take y by x, you take this point and find y by x for it. What is the geometrically, what is that quantity geometrically?
Slope.
Slope.
Slope of what? Slope, right. Slope of what? Slope of?
The curve. Slope of the curve.
Not the curve. It's definitely not the slope of the curve. It's the slope of the straight line joining the origin to that point, right? Slope of the curve is a derivative, d s and p dp. You divide the epsilon by p, what you get is the slope of the straight line joining the origin to that point. Okay? Is that okay?
Okay, sir. Yes.
And therefore, the critical in this graph, the critical velocity, what is the physical meaning of that? It's the minimum slope of the line joining a point on the curve to the origin, in which case here it would be this one, right? Any other point on the curve, say this one, would have a higher slope. The minimum is here. Okay? Right? Minimum, of course, means that it's just tangent here. Clear? So the
Yes, sir.
critical velocity can, if you have a graph like this, the critical velocity can be easily figured out. It's basically you just consider all possible chords uh, from the origin to the curve and find out the one which has the minimum possible slope. The critical velocity is the slope of that. If the velocity is smaller than that, you will simply not be able to, a curve with a slope smaller than that will simply never be able to touch the curve. So you will never be able to get epsilon p equal to minus p dot. Okay. Clear. And what is the problem with the Bose-Einstein gas? There, what is the minimum slope here? So if you take different chords, they have different slopes. But it's like as you get closer and closer to the origin, the slope vanishes, right? The minimum possible slope from of a line joining the origin to a point on the graph for t square by Poisson happens to be 0. That's why it doesn't have a critical velocity, or it doesn't have a non-zero critical velocity. But if you have a dispersion relation which looks like this, we will explain why it looks like this in the next class. But if you have a dispersion relation which looks like this, then this slope will give you the value of the critical velocity. Okay. So in the next class, we will talk about this dispersion relation for the quasi-particle excitations, Landau's original theory and Feynman's version of that, not in great detail, but at least enough to understand qualitatively why the graph looks like this and how this would actually, why this would then lead to an actual non-zero value for the critical velocity, so that superfluid flow is really possible. Is it okay? Is this idea okay that you can, that epsilon p by p, this point has coordinates p and epsilon p, right? The ratio of the two is basically nothing but y by x for this point, which is the slope of this line. You're just looking for the minimum such slope, which is just the slope of this line, which just, so you think of just turning this line like this until it just touches the curve. After that, it will not. So where it just touches the curve, that gives you the critical velocity. Right?
Yes, sir.
Okay, so Next day, we will explain why the dispersion curve actually looks like this and what significance does it have. But because the dispersion curve actually looks like this and not like the Bose-Einstein curve, E square by 2 is can actually a fluid flow through a tube without any uh, dispersion. At least once its velocity is below that critical velocity, the velocity given by this line. So we will see later that there were modifications to Landau's basic theory. But the idea is very much here. Okay. So let's meet on Tuesday next. But before we go, any other questions about what I said today? Oh, by the way, I'm putting up these videos on YouTube. I hope you have been able to first see. I have not been sending you. I send you the links for the first few, not the later ones. But that's basically because there's a playlist, and the addresses are actually in the playlist. So it's easier for you to just look at the playlist and find out the videos.
Okay, sir.
Okay, sir.
Okay, fine. Bye for today.
Thank you, sir.
Thank you, sir.
Thank you.